Right, so today we are going to discuss a very important topic, and that is called aromaticity. Okay, and I will explain you this topic in detail, and especially for JAM students, this will be very beneficial because each and every question, each and every question paper consists of questions from aromaticity, right? So we'll discuss that in detail. So I'll be discussing about aromatic compounds, anti-aromatic, homoaromatic, and non-aromatic compounds. Now, basic rule for aromaticity, like all of you know, is it must be cyclic, right? So the compound must be cyclic. That is the first rule. That is the first, you could say, thing that is required for aromaticity. That the compound should be cyclic. The second is it should follow your 4n plus 2 pi rule. That is the Huckel rule. 4n plus 2 pi Huckel rule. It should follow. Where this n is nothing but an integer. N is an integer. It could be 0, 1, 2, 3, so on and so forth, right? So basically your n is so this is the second rule, that it should follow this 4n plus 2 pi Huckel rule. So where these are in n is the number, like I told you, it could take values of 0, 1, 2, 3, and so on and so forth. So basically the system should contain these many pi electrons. For example, if n is equal to 1, so this becomes 4 into 1 plus 2, that is 6 pi. So it should consist of 6 pi electrons. Okay, this is the second rule for aromaticity. The third should be that it should be conjugated. The system should be conjugated. That means there should be alternate single and double bonds, or in basically there should be a p orbital present. I'll explain in detail what does that mean. But the third rule in general you can say is there should be conjugation. Okay. So the third thing is that there should be conjugation, and the fourth is that the ring system should be planar. So these four conditions you have to remember when you are seeing whether a compound is aromatic or not, right? Now, if I take some examples, see these kind of methods like aromaticity and these kind of concepts, they require more of practice. Okay, so or they can be explained in a better way by using examples. So I'll be taking more and more of examples and trying and help you understand. So for example, if we take benzene, so you see the benzene molecule is planar because all carbons are sp2 hybridized, and you know all sp2 hybridized carbons are planar, right? They are present in the same plane. So all of them are sp2 hybridized, so it's a planar molecule. It's cyclic, like you can see it's cyclic. It's conjugated. There are alternate single and double bonds, so there is resonance taking place. And so basically, and it has 6 pi electrons. If you count, each double bond has 2 pi electrons. So 2 plus 2 4 plus 2 6. So there are 6 pi electrons. That means it follows the 4n plus 2 pi Huckel rule as well. So it satisfies all the four conditions, and that is why it is aromatic. Okay. Now if I take some other example, let's say for example this. We have a positive charge here and double bond here. Now if you draw the resonating structure for this compound, if I draw the resonating structure, see it might look like there is no conjugation, but there is actually conjugation, because this carbon over here has empty p orbital. Okay, it has empty p orbital. So this double bond can be shifted over here, and now what will happen is we'll generate a positive charge over here, double bond, like this. Then if you draw another resonating structure for this compound, this double bond migrates like this. You have double bond over here, positive charge over here, and then again you get back the same structure. So basically what I'm trying to show you is that the conjugation is still there in this compound. It is planar. And how many pi electrons does it have? If you see, it has only 2 pi electrons, because there's only one double bond. So 4n plus 2 pi Huckel rule if we use, so we can keep n equal to 0, so we get 2 pi electrons. So it satisfies the Huckel rule as well. So it is planar, it satisfies the Huckel rule. It is conjugated, and first of all it's cyclic. So it is satisfying all the conditions, right? What happens is for a double bond, for a double bond formation, there should be presence of a p orbital, of an empty p orbital. So if a compound has an empty p orbital, then it can easily take place. The conjugation can easily take place. So here you can see the conjugation can take place. Okay. Now if I take some more examples, let's say this compound. Now this negative charge on carbon ion, the carbon ion also contributes 2 pi electrons. Okay, so whenever you see a negative charge on a carbon, the carbon ion generally it always contributes 2 electrons, right? 2 pi electrons. So we have 2 pi electrons over here, 2 pi electrons over here, 4 pi plus 2, 6 pi electrons. So 6 pi electrons are present. Okay, so that means it's satisfying the Huckel rule. You know, for Huckel rule to be followed, there should be either 2, 6, 10, 14. If you put n equal to 0, you get 2. If you put n equal to 1, you get 6. If you put n equal to 3, you get 14. And sorry, if you put n equal to 0, you get 2. If you put n equal to 1, 6. Then n equal to 2, n equal to 3, so on and so forth. You keep getting. These are the magic numbers for aromaticity. So if a compound contains these pi electrons, I mean 2, 6, 10, 14, and then so on and so forth, 18, like that. So it is aromatic. Okay. So it has 6 pi electrons satisfied. It is in conjugation. Yes. See, if you move this negative charge like this double bond moves over here. And if you draw the resonating structure for this like this, okay, then this can move over here and we can get negative charge over here. So basically conjugation is there in this compound as well, and it is planar. So generally, see, you cannot predict planarity or not, but generally 4-membered, 3-membered, 5-membered rings are generally in most cases planar until and unless there are very high steric repulsions or steric strain in the compound. In general, they always occupy a planar structure. All right. So in the latter half of the video, I'll tell you the exceptions that are there to the planarity. Like in some cases, yes, the planarity is lost. I will take those specific examples for you. Right. So this is aromatic again. Now what about let's say pyridine? See, I want to discuss one important example, and with the help of pyridine, I'll discuss that. So this compound over here is called a pyridine. Okay, it's a heterocyclic compound, pyridine. And on the other hand, let's say I'll take pyrrole. Now, if you see both the compounds, this has, if you only calculate the double bonds, it is a 6 pi system, right? 6 pi electrons. There are 3 double bonds, so 6 pi system. This over here is a 4 pi system. But both are aromatic. So for this, you can understand that there is a 6 pi system, so it's aromatic. What about in this case? In this case, if you see, we have 4 pi electrons, but we have lone pair on nitrogen as well. So this lone pair also acts as, I mean, it is basically, it has a p orbital with electrons. So this p orbital of nitrogen also participates in resonance. And once it participates in resonance, because if you see this double bond, let's take this donates electrons like this, and then if I draw the resonating structure for pyrrole, so we have a negative charge over here, we have nitrogen, right? So then again the conjugation is there, so then this contributes like this negative charge moves over here, so conjugation is taking place because the nitrogen lone pair is available for resonance, for bonding, right? So the nitrogen lone pair contributes in the conjugation, and hence we get a 6 pi system and it becomes aromatic. Okay, because it's cyclic, it's planar, and now it's conjugated and it's 6 pi system. But then why in case of pyridine are we not taking the lone pair of electrons? Because in case of pyridine also we have lone pair of electrons. So if you consider the lone pair of electrons over here, then this becomes an 8 pi system. Okay, and this is where a lot of students I see are getting confused, that in which case should we consider the lone pair on nitrogen, or in which case we should not. So there they have chances of making a mistake. So let me just clear this out, that in which cases does the lone pair of electrons participate. So it's a very simple idea. Okay, there's a concept behind it as well, but for those of you who are not looking for any concept, they just want to know in which case we should take or in which case we should not, I'll explain you in a short way. So wherever you see a double bond present on the nitrogen or on any heteroatom or any carbon, if the double bond is already present, that is, it's already participating in the conjugation. So over here, if you see, the nitrogen is already participating in the conjugation. That means one of the p orbitals of nitrogen is already participating in the bonding. So for example, if you see, if I take the same case of pyrrole and pyridine, now over here if you see, I forgot to draw this hydrogen as well. There was a hydrogen as well present on this nitrogen. I forgot to draw it in case of the pyrrole. If you see over here, this nitrogen is already uh, participating in bonding. I mean, one of the p orbitals is already participating in the conjugation. So just remember this, that, or just remember this always, that per atom there's only one p orbital can participate in bonding. So since already one p orbital, or you can say there's already one double bond present on this nitrogen, hence there would not be the lone pair will not participate in bonding again. But over here, if you see, there's no double bond next to the nitrogen, or nitrogen is not participating in double bond formation. So the lone pair can participate in bonding. But if you are clear with the orbital concept, you can see over here that one of the p orbitals is already participating in bonding, or is already participating in conjugation. That is why the second lone pair will not again lead to conjugation. Whereas over here, there's no p orbital participating in this case. So that is why it can contribute one p orbital. So always remember, a compound can at max contribute only one of the p orbitals. That is, only one of the p orbitals of the atom can participate in bonding, not more than that. Let me take another example to get more clarity. If I take this example over here, I know most of you might think this is 8 pi system, but this is not a 8 pi system. Why? I told you this negative charge also acts as a 2 pi electron, 2 pi system, right? But if you see this carbon over here, it already is, one of the p orbitals is already participating in bonding. That is, it's already doubly bonded. Okay. So in simpler terms, this carbon is already doubly bonded, so it cannot form more than one double bond. So this negative charge, or these pi electrons present on this particular carbon, are not going to participate in the resonance, and so this will be a 6 pi system and not a 8 pi system. And this compound also turns out to be aromatic. This compound also turns out to be aromatic, okay, because this is a 6 pi system and not a 8 pi system, because the negative charge on this carbon is not participating in the bonding, because the p orbital has already participated in bonding with the next carbon, or has already participated in the conjugation process. So another p orbital cannot participate, and because of that it has only 6 pi electrons, and hence it's aromatic. Okay. Similarly, if I take the case of this compound, let's say this hypothetical compound, if I take, we have oxygen, and so there is a positive charge on the oxygen. So again, it is a 6 pi system. Why? Because we have 3 double bonds, each of them are contributing to 2 pi electrons each, so we have 6 pi electrons, but we have lone pair on this oxygen. Okay, so one of the lone pairs is already participated in the resonance process, but we have one lone pair present. So this lone pair is not going to participate again, because one of the lone pairs, or it is already forming a double bond with the carbon. So it's already, one of the p orbitals is already participating in the resonance process. So another lone pair will not participate in bonding, and it's aromatic. Easier way to show, a tricky way to show this compound will be like this. Okay. Right. So if you see this compound, you might think that it is not aromatic, right? But indeed it is aromatic, because this lone pair is going to participate, and this will be the resonating structure for this. So always remember to see if the compound has a lone pair of electrons or not, if the atom has a lone pair of electrons or not, and then see whether it's already doubly bonded or not. So if it's already doubly bonded, then the lone pairs are not going to participate in resonance. And just to gain even better clarity, so that you never forget this, let's take the example of imidazole. So this compound over here is called 5-membered ring with 2 nitrogens, is called imidazole, and we have double bonds over here, right? So which of the lone pairs, this nitrogen also has a lone pair, this nitrogen also has a lone pair. So now, right now it's a 4 pi system. So which of the lone pairs will participate in the aromatic or in the bonding process or in conjugation to get the resonating structures? This nitrogen over here will participate. Why? Because this one is not doubly bonded to any carbon, so this nitrogen can have p orbital conjugation with rest of the atoms. Whereas this nitrogen is already forming a double bond with the carbon, or its p orbitals are already participating in the conjugation, and hence it will not participate again, right? So now I hope that you have got the clarity with this kind of concept, and now we'll move on to anti-aromatic compounds. Okay, anti-aromatic. So what is anti-aromatic? Um, just let me check first whether the video is filming or not. Right. Okay. I think I'm writing it to a little above than the usual, so sorry for that. Anyway, so I'll make this line as the, so I'll write everything below this line. So we have anti-aromatic compounds. Now in anti-aromatic compounds, the same thing happens. It has to be conjugated. Okay, it has to be cyclic, and it has to be planar. The only exception is, instead of the 4n plus 2 pi rule that I have just discussed, it should follow 4n pi electrons. It should have 4n pi electron system. So instead of the usual 4n plus 2 pi that I've discussed for Huckel, I mean that is the Huckel rule, it should have 4n pi electrons. And anti-aromatic compounds, as opposed to aromatic, are very unstable. Aromatic compounds are highly stable because of the aromaticity, whereas anti-aromatic compounds are very unstable, and most of the compounds, they tend to dimerize. Okay, so like if I take the example of this compound, so over here if you see, it's planar, it's cyclic. Okay, it's conjugated. You can see all the our carbons are sp2 hybridized. See, a general case to see whether a compound is conjugated or not is that it should not have a sp3 hybridized carbon. That's a general case. There are certain exceptions which again I'm going to discuss, but in general, if you have to see whether a structure is conjugated or not, you can see whether all the compounds are sp3 hybridized or not, all the carbons are sp3 hybridized or not. But that is a very general thing. There are a lot of exceptions to this thing, right? So this has 4 pi electron system. So that is why this compound over here is anti-aromatic. It's anti-aromatic. Okay. If I take another example, I'll just draw below this only. So for aromatic, I had taken this compound. This compound was aromatic because it had 2 pi system. Instead of this positive charge, if I take negative charge over here, now this becomes anti-aromatic. Why? Because now instead of a 2 pi system, it's a 4 pi system. All other things are same. It is cyclic, it's conjugated, and it's planar. But now it has a 4 pi system. How? And if I draw the resonating structures, so negative charge comes over here, and then you can draw all the other resonating structures. But in general, if you see, this is a 4 pi system, and hence this also becomes anti-aromatic. So compounds, so structures like these are anti-aromatic. Okay. One more example, if I take, if I take cyclopentadiene anion, this is aromatic. Why? Because this is a 6 pi system. Because these two double bonds contribute 4 pi electrons, and this negative charge also contributes 2 pi electrons. And it is in conjugation, because if you see this negative charge, if you draw the resonating structures, I do not want to waste my time on drawing the resonating structures. You will see that it's in conjugation, it's planar, it's cyclic, and it follows the 4n plus 2 pi Huckel rule because it has 6 pi electrons, so it's aromatic. But instead of this negative charge, if I take cation, cyclopentadiene cation, this is anti-aromatic. Why? Because still the conjugation is there, because this carbon has empty p orbitals. So this double bond can migrate like this. Okay. And if this migrates, we have, this is conjugated. Okay. I'm just trying to show you that this is conjugated. We'll have positive charge over here, and the positive charge will then rotate according to the resonating structures. So this has 4 pi electrons. because this has 2 pi, this is contributing 2 pi, two double bonds contributing 4 pi electrons total. So we have 4 pi electrons in total, and it is following all the other conditions. That is, it is cyclic, it's conjugated, it's planar, and it's following the 4n pi electron rule. So it is anti-aromatic. Okay, so this is the main difference between aromatic and anti-aromatic. Just remember, all the things are same for aromatic and anti-aromatic. Only thing is it will follow 4n plus 2 pi aromatic, and anti-aromatic will follow 4n pi electron rule. Okay. Now let's take non-aromatic. Non-aromatic compounds. Non-aromatic. What is non-aromatic? Some might wonder that all compounds are non-aromatic if they do not have aromaticity. Even aliphatic compounds are non-aromatic. That is not the case. Non-aromatic have certain different criteria. Okay. Let me take an example to explain non-aromatic compounds. If you take this compound over here, you see this carbon over here is sp3 hybridized. So conjugation is lost. But it has 2 pi system. That means it is following the Huckel rule. It is a 2 pi system, so it's following the Huckel rule. It's cyclic. Okay. It's planar as well. Sorry, it's cyclic and it's following the Huckel rule. Okay. Right. So it's cyclic, it's following the Huckel rule, and yes, planar as well. Like, not technically, I mean, okay, let's just avoid this thing. So it's Huckel rule and cyclic. Okay. The only problem is it's not conjugated. So compounds which follow rest of the criteria but are either not conjugated or are not planar are non-aromatic. That means they follow the 4n pi rule. They can follow the 4n pi rule. Just listen to me carefully because this is important. They follow the 4n pi rule or the 4n plus 2 pi rule. They follow one of these. So they follow one of these rules. Either they are 4n pi electron systems or 4n plus 2 pi electron systems. They are one of these. But the only problem with them is, and they are cyclic as well. But the only problem is that either sometimes they are not conjugated or sometimes they are not planar. Like in this case, I can say that it is not conjugated. There is a break in the conjugation because of the presence of this sp3 hybridized carbon. So there is a break in the conjugation, right? But but they are following the 4n plus 2 and the 4n pi electron system. Let's take another example, and this compound over here, cycloocta. This might fall, and if it falls, then I'll do another video on this topic. Okay, but there's a high chance this phone is going to fall. Anyway, compounds, what happens is, like I told you, 4n plus 2 or 4n pi system is followed, but either it's not conjugated or it's not planar. Now in this case, most of you might have been taught in the class that this compound over here is anti-aromatic. Why? Because this compound is planar. Okay, this compound over here is planar. That is true. Okay, there's conjugation over there. All the carbons are sp2 hybridized, so there's conjugation also there. So it's following the 4n pi system. It's following the 4n pi system. There's conjugation also, and it's it's cyclic as well. Okay, but so, and apparent once you look at the structure, yes, this structure is planar. So they might tell you that this compound is planar as well. So it's planar. It's following all the rules for anti-aromatic compound. So they tell you it's anti-aromatic, but actually it's not anti-aromatic. If you see the real structure of this compound, the actual structure, it's not planar. And why is it not planar? Because I told you that anti-aromatic compounds are highly unstable. So to get rid of this instability, this compound adopts a non-planar structure. And what does the structure look like? So the structure of the compound is like this. So if you see, it's like a tray. Okay, it's like a tub or a tray, whatever you like to call it. Like there are two sides to it. Like if it's like this and then this. Okay, like that. So this is the structure, the real structure for this compound. So this is actually not anti-aromatic, but this is non-aromatic. So to get rid of the instability that an anti-aromatic compound has, it adopts a non-planar structure, which because of which it becomes non-aromatic. So non-aromatic compounds as compared to anti-aromatic are more stable. I mean, aromatic compounds are the most stable, followed by your non-aromatic and then anti-aromatic. So to get rid of the extra instability that the anti-aromatic compound was providing, it adopts a non-planar structure, because of which it becomes non-aromatic. So the only difference between non-aromatic and aromatic compounds, or non-aromatic and anti-aromatic compounds, is that they are either not conjugated or not planar. A non-aromatic compound could follow 4n pi rule also, and could follow 4n plus 2 pi Huckel rule also. So there is no restriction on the number of pi electrons for non-aromatic compounds. The only thing is there should be either a loss of conjugation, or there should be non-planarity for the compound to become non-aromatic. Right? Now we'll discuss about homoaromatic compounds. Now in case of homoaromatic compounds, what happens is we have so we'll discuss about homoaromatic compounds. So again, I'll take the same case. Okay, let's say right. So you add H plus and you get this compound. If you add H plus to this compound, I'll just draw over here. You get a positive charge over here and you get hydrogen attached. So basically this is the structure, and you have two hydrogens over here. Now you might think that this compound is, I mean, this is sp3 hybridized carbon, so it is and non-aromatic, because it's I mean, there's loss of conjugation. It's a 6 pi system, but there's loss of conjugation because of the presence of this sp3 hybridized compound. But what happens in reality is okay, just a second, right? Yeah. So what happens in reality is, if I draw the structure, there's a positive charge over here, and you can imagine this carbon over here, it's going out of the plane. Okay, or I'll show it by bold bonds. So this carbon over here is actually going out of the plane. Okay, and this double bond is actually participating, or is actually interacting with this positive charge. So this compound, if you see, if I ignore this carbon which is above the plane, if you see only this compound till here, till this point, it is a 7-membered ring, but it's conjugated because this double bond is interacting with this positive charge. So it is not totally aromatic compound because of the presence of this sp3 hybridized, but because this sp3 hybridized carbon has gone above the plane of the ring. So this whole structure is in the plane of the ring, and this carbon that I have drawn is above the plane. So it kind of attains a planar structure, and this double bond can interact with this positive charge to gain some kind of stability. So that is why these compounds are not totally aromatic, and hence they are called as homoaromatic compounds. So if you see the stability, we have aromatic compounds which are the most stable, followed by your followed by your homoaromatic, then we have non-aromatic, and then we have anti-aromatic. So this is the stability. So sometimes you can be asked in the exam a question on the basis of this, that you could be given 4 structures and they would tell you to write the stability of these 4 structures. So you have to see which one is aromatic, which one is homoaromatic, which one is anti-aromatic, and which one is non-aromatic, and then give them the order of stability. One thing that I forgot was actually I forgot to draw one structure which is again aromatic, is your tropylium ion. So if I draw the tropylium ion, that is a 7-membered ring. Okay, so we have 1, 2, 3, 4, 5, 6, and then your 7, right, like that. So this is your tropylium ion. It's a 7-membered ring with a positive charge. This is known as your tropylium ion. Tropylium ion. So this is also aromatic. Why? Because we have MTP orbital over here, and then there's no breakage in conjugation. It's a planar molecule. It's cyclic. It's following the 4n plus 2 pi Hucker rule because it has 6 pi electrons, and there's no break in the conjugation. So this is aromatic. Similarly, if you see this compound and this compound, if you try to relate, this is 1, 2, 3, 4, 5, 6, 7. This is the 7th carbon. So it is like a tropylium ion with this carbon hanging above the plane of the ring. So this carbon over here is hanging above the plane of the ring, and this hole is like acting like a tropylium ion. The only difference is there's one carbon which is hanging above the ring, above the plane of this ring. So there is some kind of aromaticity present, but it is not, you cannot call it a totally aromatic compound. So hence they have given it a name called Homo aromatic compounds, right? So they are stable, but not as stable as aromatic compounds. And there are many exceptions to, not exceptions, but there are certain peculiar cases that I want to discuss. But I think this video is already very long, and so I'll discuss those topics again in my next video. So please stay tuned for that video, and please like, subscribe and share to my channel. And I hope you like this video, because I have tried to explain each and every concept related to aromaticity over here. And once I make that video based on the based on some you can say exceptions, some exceptional compounds that are there, you might then you are good to go for any kind of entrance exam or any kind of question. You are good to attempt any kind of question based on aromaticity, right? So thank you so much.